We're going to continue looking at polygons by talking about congruency. So when things are congruent, they have both the same shape. So if you look at these, they have the same shape in all of these pictures and the same size. That's why this pair here and this pair here and this pair here are all considered congruent, but this last pair here, the same shape but they're not the same size, they are not congruent. That's actually called similar, but it's not congruent. Thing about congruent shapes, you're allowed to turn them or rotate them. You can see how these are rotated. You're allowed to slide them to translate them to a new place, so I can take this and slide it over. You're also allowed to mirror them or flip them. So whenever you take something against a reflection line and reflect it over that line, that is okay. So all those things can be done and it's still considered congruent. This next part here, CPCTC, we're going to use that word, that short name a lot. CPCTC, kind of a tongue twister. It means that corresponding parts of congruent triangles are congruent. What it means is that if you have two triangles that are congruent, all of their parts are congruent. If you say that triangle ABC, I'm going to write this out here, triangle ABC is congruent to, equal sign with a little squiggly above it, is congruent to triangle DFE, and I'll explain why I picked that particular order, DFE, then all of the corresponding parts are also going to be congruent. So that means that the first letter, A, and the first letter, D, are going to tell you that angle A equals angle D. And we can see from our picture, angle A does equal angle D. It also means that angle B is going to equal angle F. And that's why I wrote it in the order I did. I didn't say DEF, I said DFE. Because angle B is not equal to angle E, it's equal to angle F. And let's go ahead and check that out. We have F here, we have B here, both of them double line, so that checks out. So angle B is equal to angle F. And then what would obviously follow, C and E, so angle C and angle E. And write that in there. Angle C and angle E. Now you also get your line segments out of this too. So we take our first two letters, AB and DF. So AB right here, redo that, AB and DF, you can see both of those. That was not DF. They both have double tick marks on them, and that's how you know that they are congruent. So they also are the first two letters, so that's how you know that they are congruent here. So AB equals DF. And you can keep going. I don't even need the picture, even though I can see that AC and DE are congruent based on the picture. Since I wrote out my congruency statements correctly to start with, I don't need that. I can just look at my first and third letter and my first and third letter and say that AC equals DE. And then my last one is going to be my last two letters, so BC equals FE. I encourage you to always write it in the same order you see it here. So if it's first letter, second letter, write it first letter, second letter, not second first. Often you can get away with that, but just in general, if you're forming good habits, first letter corresponds to first letter, second to second. So let's jump into some practice here. We have polygons ABCDEF and GHIJKL. We're told that they are congruent. So this shape and this shape are the same exact shape and the same exact size. So which side is congruent to CD? Well, C is the third letter, D is the fourth letter. So then the side that's going to be congruent to that is going to be the third letter I, fourth letter J. So CD is congruent to, or I will just say equal to for sides, IJ. Next thing you're told here, number 2, ABC is congruent to DFE. List all the congruent angle pairs and side pairs that you now know as a result. Well, since we wrote them up here, we're actually just going to point up here. But the idea is that the first letter and first letter, A and D, F and B, C and E, and then all the pairs of two letters that'll form your sides. This right here is called the Isosceles triangle theorem, and you'll notice I didn't put in a lot of information, I just put a picture for you to start with. I'm going to describe it visually first, and you can decide if it would be easier to write out in words. But let's imagine you have a triangle. And isosceles triangles, as you can see from this picture here, have an equal angle at the base. They have two equal angles. They also have two equal sides next to those angles. So that's an isosceles triangle that we're always used to. If you know that you have two angles in a triangle that are exactly the same, you know you have an isosceles triangle. It tells you that you're going to get these sides for free. So if you knew the angles, you automatically know the sides now, because isosceles triangles will always have both of them together. You'll either have both or neither. So if the two angles are the same, the two sides are always going to be the same. And from the same token, when you have an isosceles triangle and the two sides are known to be the same, you get for free that the two angles are the same. So you get the full package of an isosceles triangle. Basically, the isosceles triangle just says if you have angles, you get the sides. If you have the equal sides, you get the equal angles. So let's go down to some practice. I think this is one that's easier to understand with practice. It says solve for x. Here in your picture, you're told that these angles are the same. So what that tells me for free is that this side equals this side. In other words, in this problem, 15 equals 4x plus 3. So let's go ahead and solve for x. So 15 equals 4x plus 3. We take away 3 from both sides. So then 4x equals 12. And then we're going to divide both sides by 4. And we get 3 is equal to x. So solve for x, x equals 3. This next one here, it says solve for x and y. We are given that these sides are the same. So that means we get that the angles are going to be the same. Which means that I can say that this 3x minus 11 is equal to this 2x plus 11. So 3x minus 11 equals 2x plus 11. Now don't get caught up about the fact that it says solve for x and y all at once. There's a lot of things to work through in this problem. Let's start with what we know for sure to be true, and that's this right here. We take away our 2x from both sides, and we add our 11 to both sides to get everything, x on the left, numbers on the right. And when we do that, we get x, these go away, equals 22. So x is equal to 22. Now how are we going to get y? Because we don't know anything about 2y is equal to. So y is going to be a little bit of a problem at the moment. Since we do know though, we know x, we have that done, we can go ahead and plug this in. And if we did this right, since this is isosceles triangle, these two things when we plug it in better be equal. So 2 times 22 is 44, plus 11 is 55. So that's 55 degrees. Over here, 3 times 22 is 66, minus 11, also 55. So we probably did that right. Now 55 and 55 is 110 degrees, leaving us with 70 more up here for the top of the triangle. If this top of the triangle has to equal 70 degrees, and it also has to equal 2y, we can go ahead and write that as an equation, divide both sides by 2, and all of a sudden, there you go, you're going to have y. So y is equal to 35. So x is 22, y 35. And that's all for section 1.